Hi, welcome back to this course on computational thermodynamics and kinetics of materials. The last couple of classes we covered something about the basics of kinetics of materials. Today we will see how computational kinetics is done. Basically, we need thermodynamics also to do this, so we call it computational thermokinetics. Let's see about that. Okay, these are going to be the contents. An introduction to what is this computational thermokinetics. We already talked about mobility in the last classes, and we will use that and see some more details of that and why to use mobility in kinetic databases. We will see that in little more detail in this class, and the concerns with regard to kinetic databases status currently and how to do this mobility assessment. The input data and models will cover. The procedure of optimization remains largely similar to how it is done in thermodynamic assessment, so we will not cover that. Then once the database is ready, how to do the simulation, basically how mobility data are used. So here we will see why it is used, and here we will see how it is used. Then one particular case which will be more frequently occurring, that is simulation of phase transformations, where we will be using something called as moving phase boundaries. Okay, so in that, this idea of local equilibrium is quite important. We will see what are the basics for that. Okay, the kinetics of various processes can be simulated. Simulation of diffusion controlled processes are what we will be doing. These diffusion controlled processes are covering a large portion of solid state transformations. So we will be able to simulate such things. There are transformations which are not diffusion controlled, and those things cannot be simulated in this. Couple of important categories I'm going to put here: homogenization and diffusion controlled phase transformations. In both these cases, diffusion is the predominant mechanism. So in these cases, what we have to do is solve Fick's laws. We have talked about it with an example of carbonization in the previous class, and the same thing needs to be done here as well. So if we have to solve Fick's laws, we need to know the mobility information, that is the kinetic database. We need that, and we also need thermodynamic database. Hopefully you can see why it is required, because there is a thermodynamic driving force for these diffusion controlled processes. So we need to take that also into consideration. So both the databases are required. Thermodynamic database is what we have used for all the thermodynamic calculations that we have done. So you know quite well about this. We will see more about kinetic database today. While using these kinetic databases, we'll be using mobility instead of diffusivity, because diffusivity data pose problems. We'll see about such problems. And mobility data is a superior alternative. Okay. In CalFAD, mobility is modeled and assessed in a similar mathematical way as Gibbs energy. This is one of the biggest advantage of mobility. Okay. We will compare this diffusivity and mobility. We have done this in the last class, where we see that mobility comes here along with the driving thing. This is the thermodynamic factor which drives, where chemical potential gradient is given, and in general what we saw about the Fick's laws is concentration gradient and how it affects the flux. This can be experimentally measured. If there is any concentration gradient, we can see what is the flux, we can calculate what is the diffusivity, things like that. But when we talk about thermodynamic driving force, so that aspect cannot come directly in this. So this is more like, this is the concentration gradient and this is the flux, so this is the diffusivity. So this information can come from the experimental measurement. What cannot come is in this flux, how much is driven by thermodynamics. So that aspect is not there. When it comes to mobility, that's what we are dismantling. Mobility talks about the movement of atoms with respect to a unit driving force. Okay. Okay. So in the for ideal solutions, we said mobility and diffusivity are very simply connected with this RT term. For non-ideal solutions, there is a thermodynamic factor coming, and this thermodynamic factor is related to the driving force. Let's see more about this mobility. Mobility can be split into two parts: a frequency factor MB naught and an activation enthalpy QB. Okay. It's similar to the diffusivity. MB is MB naught exponential minus QB by RT. In this form it can be written. You see, it looks largely similar to diffusivity, because if we talk about mobility, we say a mobility related term multiplied by the chemical potential gradient. This is what is going to decide the flux. But when we put the chemical potential gradient, it takes care of the driving aspect. But still the other aspects, the activation energy part, is going to remain in the mobility part. So it has to have the format of the diffusivity, where a frequency factor, a pre-exponential factor comes, and activation energy comes. So we need to model these things in order to use mobility in the databases. We need to model these things. We will see about that shortly. Why to use mobility in kinetic databases? In multi-component systems, many diffusivities must be determined. When we talk about diffusivities, many diffusivities must be determined, and it can come from having different concentration gradients in the material. It is going to depend on that. Okay, so that has to be determined, and more importantly, these diffusivities depend on alloy composition and are often interrelated, making the database very complex. So keeping database made of these diffusivity values is going to get very complex. Okay. A better approach is to store atomic mobilities in the database instead of diffusivities. If we do this, we have some advantages. This reduces the number of parameters that must be stored and ensures the parameters are independent. Because we are going to say that the thermodynamic factor is separate and it will come from thermodynamic databases. What is required is only these other parts, the activation energy and the MB naught part, that has to go into this mobility side. Therefore, it becomes simpler. We need not store this thing. We can only store this thing. So that is where mobility databases become more elegant to use. The required diffusivities for simulations can then be calculated as the product of a thermodynamic factor, which comes from thermodynamic database, and a kinetic factor, which comes from mobility database. So eventually diffusivities will be calculated from that. We will see how to use mobility kinetic databases shortly. That time I will explain more on this particular aspect. So if you recall the Onsager formalism, where we had this thermodynamic factor, this is essentially the second derivative of molar Gibbs energy with respect to concentration. So it can come from Gibbs energy database. The thermodynamic factor can come from Gibbs energy database. That's what we are essentially saying. The driving part can be calculated from assessed Gibbs energy database. And the kinetic factor depends on atomic mobilities, which can come from assessed mobility database. So we need both of them in order to do these thermokinetic simulations. So there are a couple of big concerns with this kinetic database, which I am going to list now. So far there is much less mobility data which has been systematically assessed like the thermodynamic data. Okay, so not a large number of systems are assessed for mobility. That is one big problem. Second big problem is there is no SGTE kind of standardized data. Okay. Even for unary element, one element diffusing in the same environment, even for that there is no standard data available. Okay. Therefore, mobility assessment has to be done. I am going to spend few slides on how it is done, basically the input data and models. So we need to have, just like the thermodynamic assessment, input data on one side, any data that is related to diffusivity can come here. So we can get the diffusivity data. Concentration profile can also be directly used. There are methods for that. And these things, once they are available, we can have these models on the other side, mobility models for composition temperature and pressure dependency. Okay, so mobility depends on these things. So that is why we said mobility can be written in the form of Gibbs energy. The dependencies can be similar to what the Gibbs energy dependencies are. So mobility dependencies can be modeled in one side. So once these things are done, we go for the statistical fitting, where models are fitted to input data and the output is mobility descriptions or mobility database eventually. So let's see what are these different input data. First type, diffusivity data coming from tracer diffusion. Tracer diffusion is one very special technique where we use radioactive isotope tracers, okay, for self-diffusivity of a single element, for example nickel in nickel, or for impurity diffusivity using tracers. Impurity diffusivity term is used when an element is added in tiny amount to an environment and see how this is diffusing. That is called impurity diffusivity. Okay. Basically, why we are using radioactive isotope, you can see from this itself, nickel in nickel. Let's say you have a nickel atom sitting nicely in a FCC lattice, and you want to know how fast a nickel atom will diffuse from one end of this material to the other end. Okay. So this nickel atom that is entering in one side, how do you know the same nickel atom is coming in the other side? Because everything is nickel, right? So in that way, you need to have an isotope of nickel where electron structures and everything are going to remain largely the same. In the nucleus, there are possibly some extra neutrons. So they make the atom to an isotope, and that isotope is going to be radioactive, and that radioactivity can be measured. So that is the tracer that we talk about, radioactive tracer. That is an isotope basically. That is put on one side, and its diffusion is tracked based on the radioactivity at different slices of material at different times. Okay, this is called tracer diffusion, and that is used especially for measuring the self diffusivity as well as impurity diffusivity. This impurity diffusivity can also come without tracers, and that is obtained by diffusion of a small amount of element I in a solvent J. Because this is nickel and this is FeCr kind of thing, we can still track how this impurity is diffusing. Therefore, for impurity diffusivity measurement without using tracers, this technique can be used. It's normal diffusion of an atom, not an isotope. Okay. This is another technique, interdiffusion, which is obtained from diffusion couple experiments. Interdiffusivity we can measure. That's called as effective diffusivity. It's not diffusivity of one element, because when we say diffusion couple, we have seen examples of diffusion couple. You join couple of different metal pieces together and they interdiffuse into each other, right? So in that way, what we measure is an effective diffusivity, not the individual elements diffusivity, and that can directly come from interdiffusion studies. And these interdiffusion studies can also be used, diffusion couple can also be used to measure something called as intrinsic diffusion. This is for species specific diffusion relative to the lattice, meaning we said in this the interdiffusion studies, effective diffusivity comes directly, right? Intrinsic diffusion can also come, but we need to use the diffusion couple experiments. We need to use something called as markers, like Kirkendall markers. You can look what is Kirkendall markers later, and that can be used to figure out a species specific diffusion, not the effective diffusivity. Okay, so that is called as intrinsic diffusivity. So these are different terms: the intrinsic diffusivity, effective diffusivity, impurity diffusivity, and self diffusivity. Different terms are used. They all mean different things. Okay, all of them can be input data for mobility assessment, and concentration profile data can also be directly used. Right. So when it comes to models, we have seen that mobility can be split into these parts. Okay. So here, to keep this MB naught in the mathematical forms used for Gibbs energy, what is done is it is converted to this form, RT natural log of MB naught. If we put this, then this is more like an energy. R multiplied by T is some kind of an energy term, multiplied by MB is converted to natural log of it, so that this gives a measure of MB naught. So this entire term can be used instead of MB naught, and this will be modeled rather than simply MB naught. Okay, so how it is done? This MB naught should be converted to RT ln MB naught. So to include this RT, divided by RT, and to include this natural log, you keep an exponential outside. Therefore, this entire thing means only MB naught, nothing else. But only this part is modeled, and this thing will be calculated outside the database. So division by RT and taking exponential of this data can be done by the routing. It need not be stored in the database file. Okay. Also has to be modeled, and this part is anyway energy. This can be modeled like Gibbs energy. Okay. So these two terms which look like Gibbs energy are modeled in the following form. Phi b means both of them. Here phi b is RTL and MB or QB. So both of them are modeled in this manner using RK power series. You can see Redlich crystal parameters can be used. Here you can see instead of L that we have been using L parameter in thermodynamics, we are putting this phi b ij r. So this is the interaction kind of thing that we used in the thermodynamics. Here it is for mobility. Okay. So single element data, single element activation energy is here, individual element activation energies. So they are like the reference Gibbs energies. So they are here, and then if elements interact, this term should come, and a composition dependency terms are here, and this term will be having the temperature dependency, and if pressure dependency is modeled, it will also have pressure dependency. Okay, so phi b here is either RTL and MB naught or QB. So both of them separately are modeled like this. Okay, then phi b I, this term is the reference term, which is the pure I's phi b value, and this can be temperature and pressure dependent term like the SGTE data for thermodynamics. And then phi b ij, or this is the mobility interaction parameters, and they can be also modeled as temperature dependent expressions. Okay, or if the pressure dependency is there, that can also be modeled. Okay, based on magnetic ordering, more factors can appear in the model, but the notations are like this. In the setup file or database file, this is how we will be seeing things. If there is no magnetic ordering, this is a quite simple expression. I am putting only this. By in magnetic ordering, some more terms will come along with this. So this MQ is equal to minus QB plus R multiplied by T multiplied by natural log of MB naught. So you can sense what parameter is this. So both of them together are modeled into one single sentence, that is MQ is the name given to that, and you can sense this is a temperature dependency already. And this QB is the activation energy part that can also have temperature dependency. Right? So about optimization, I am not going to spend too much of time. Once the setup file and input file are ready, the statistical fitting is similar to the thermodynamic optimization, and output is going to be mobility database instead of Gibbs energy database. Okay, so once the database is ready, simulation is done. Basically in the thermodynamics we call it thermodynamic calculation. Here also we can call it diffusion calculation, since the entire transformation process is going to be simulated virtually. We are calling it a simulation. So this is essentially about how mobility data are used. Of course, thermodynamic data is also important in this, you know that. In the simulation, concentration profile is set up, dou C by dou X. You see, when we take a material and we want to know how the material's concentration profile is going to evolve with time, that is basically the kinetic simulation. So this initial concentration profile is set up by us in the software. So this is the one which is going as an input from outside. Okay, so this is something that we set up. Then what is straightforward to calculate from kinetic and thermodynamic database? We can see that. See, d mu I by dou Cj. See, that is chemical potential for different concentrations. Okay, how the chemical potential varies with the concentration. This can come from composition dependency of Gibbs energy, right? So chemical potential comes from Gibbs energy, and for different concentration materials, what is going to be the chemical potential can come from Gibbs energy's dependency on composition. That can come from thermodynamic database, right? And what comes from kinetic databases is mobility information that will be connected shortly in this. What is available to simulate, what is available in the question, we have set up something here, right? So that is the one which is given in the question. Dou C by dou X, initial concentration profile is given, and that's what is going to evolve with time. And what calculations routines to do to calculate that? For this concentration profile, we have some concentration profile. Calculate how the chemical potential varies. Okay, how to do that? We are basically asking how the chemical potential varies with respect to distance. If you want to know this, we can use the differentiation rules and bring this dou C in the denominator here and the numerator here. So dou mu by dou X is written as dou mu by dou C multiplied by dou C by dou X. If you do this, there is an advantage. You see, this dou C by dou X is something that comes from the question itself. Alright, so we have it. And this dou mu by dou C is how chemical potential varies with respect to concentration. So if we have the concentration from the question, we can calculate how mu changes with respect to concentration. So this comes readily from the thermodynamic databases we said. So if we put these two things together, then we get how chemical potential varies with respect to distance. So if we have this data, how chemical potential varies with distance, you know, this is what we have put in the Onsager formalism, where we have this data as the thermodynamic factor, kinetic factor, which comes from mobility. Okay, these two things we can put together and calculate the flux. So now here mobility database comes and connects elegantly to this thermodynamic factor. And we can use this thing to calculate the flux. If you want to calculate diffusivity from this, make a diffusivity matrix for multi-component system and use it with the concentration profile, we can also do that. Right. Now, if in simulation of diffusion control processes, when it comes to especially phase transformation simulations, we have this moving phase boundary problems. What are they? Product phase grows at the expense of parent phase. In that way, an interface exists between parent and the product, and that interface moves. Let's say product has to form to certain volume consuming the parent. If that has to happen, then the parent should shrink and product should grow. So the interface should be moving between the parent and product. If that interface is tracked, then it means that we are simulating the phase transformation. And in that interface, at the interface, parent and product must remain in equilibrium. And we call it local equilibrium. We'll see about that. If you see here for local equilibrium, let us focus on this example. 0.15% carbon steel at 800 degrees. Okay, this is iron carbon diagram focusing on the low carbon region. 0.15 is somewhere here, and for that particular carbon content steel, we have this concentration profile here. This is the material, let's say the orange one is the material now. Percentage of carbon versus distance graph is superimposed on that, and this red line gives you the initial concentration. It is 0.15 throughout. Okay, this is how the initial material is because it is at this temperature. Okay, this is the overall composition and it is at this temperature initially, let's say, and it is completely austenite here. And from there, we are going to bring it to 800. So 800 degrees Celsius, we are going to keep it. The moment it comes from here to here, it will have this single phase. And with respect to time, you know what should happen. Alpha phase should come from this gamma. So this is entirely gamma, and from gamma, alpha should nucleate and grow to some extent. How much extent? If you put a tie line, based on the lever rule, we can figure out how much should be alpha, how much should be gamma. So this alpha content should be significantly high. This length divided by total length will be the alpha content, right? So alpha is here, this side. So that much of alpha should form, consuming so much of gamma phase. And more importantly, this tie line tells you what should be the composition of two phases. When alpha and gamma form, the composition of alpha should be as indicated by this point here in the tie line. Very low carbon. This is not a 0.15. This is much less than 0.15, 0.02, something like that. And for gamma, it is pretty high, beyond 0.4. So this is how the compositions of two phases will change. But as alpha forms, what should be the composition of alpha and gamma at the interface? At the interface, alpha and gamma are touching each other, right? It means they cannot have any other composition than the ones that are indicated by the tie line. Okay, this is how it should be. See it here. So carbon content in the alpha phase is very low, especially near the interface. If you see, it is this value. It is much less than 0.15. 0.15 is somewhere here. So this is somewhere very, very low. I am putting it slightly above actually to see it properly, but it should be very, very low, 0.02 or somewhere there. And that is the composition of alpha. And where gamma touches this alpha, you see where the composition of gamma goes to. So gamma has this more than 4. So gamma has this more than 0.4 percentage of carbon, essentially the one indicated by this tie line here. So this much of carbon should be there at the interface of this gamma alpha. So in the gamma phase, it should be this much. Only then gamma and alpha can touch each other. Okay, that's what we say when two phases are in local equilibrium. At where they are touching, we call it local equilibrium because at that point at least they have the compositions indicated by the tie line. Okay, and beyond that, you see the composition of gamma, carbon content goes down and eventually reaches the overall composition that we initially had. What will happen here is there is an interface forming here, and as alpha grows with respect to time, this interface will move. As the interface moves, there is this alpha growing which has very less content of carbon. Therefore, all the carbon from this blue region will be rejected into the orange region. So gamma will get enriched in carbon, and throughout gamma, the equilibrium composition of gamma will be attained somewhere near 0.4. That will be attained. So in the process, what will happen is this composition here, whatever carbon content is here is going to get increased. Okay, already carbon is higher here compared to this region, but thermodynamics tells this carbon content should increase further. Okay, so this will increase and reach the equilibrium composition of gamma throughout. Okay, until then this interface will be moving. It's called a diffusion controlled process because the entire movement of interface depends on how fast this carbon atom can move between this gamma and alpha phases. Okay, to impose this local equilibrium also we need to have some important ideas. So if let's keep this diagram here, the composition of this element, let's say some element K here, should be this much, for example carbon, and here in alpha phase it should be this much, right? So we can put some notations for that. And the boundary migration, the movement of this interface is called as boundary migration, is calculated by the rate of diffusion to and from the interface. This is what going to decide the movement of interface. To conserve the number of moles of a component K, a flux balance equation must be satisfied. This is imposed by this local equilibrium. If you see, velocity of this alpha gamma interface, V alpha gamma, this is interface migration rate, or you can call it velocity. Okay, this interface migration rate is given here multiplied by composition of that element in alpha minus composition of that element in gamma. It should be equal to the flux of that element in alpha minus flux of that element in gamma, right? So the flux cannot be anything. The alpha gamma phases, if they are to maintain this local equilibrium with the right compositions, they should have flux of carbon in them in this manner. Okay, the velocity cannot violate this condition. It cannot grow at any higher rate or lower rate compared to what is seen in this particular equation. So it has to maintain this. The flux is balanced. That's why we call this flux balance equation. And this is an important thing to note when it comes to local equilibrium. Thank you. I hope the lecture is useful. See you in the next class.